If you're one of the cool kids in electronic design today, you're not just designing embedded systems. You're designing wearable embedded systems. Yep, wearable devices are some of the most important things that are communicating with each other on that internet of ours. And from fitness monitors to watches to sensor equipped socks, these new devices need to gather and process lots of data from sensors. But conventional embedded processors are really pretty terrible at that kind of signal processing. They burn too much power, or they're just too slow, and it's kind of like using one of those big farm tractors to mow your lawn. They're just not well suited for the task. What you really need is a processor that's customized and optimized to do exactly the job at hand. Hi, I'm Amelia Dalton, host of Chalk Talk. Today, my guest is Chris Rowen from Cadence Design Systems, and we're going to look at Tensilica Fusion DSP, optimized processing solutions for analyzing all that data that will be spreading around the IoT. Before we get started, don't forget to click that link. There you can find out even more information about Tensilica Fusion DSP. Hi, Chris. Thank you so much for joining me today.
Well, it's great to be here. Thanks.
So there is a ton of hype around IoT these days, but IoT isn't all hype. There are actually some really interesting technologies and market trends happening in our industry, right?
That's right. IoT has certainly been talked about so much over the last year or so, but it really is also a place where some significant innovation is taking place, and it's driving a lot of new electronic design. I see IoT as really being this idea of distributed services based on gathering, sensing a lot of new kinds of data, consolidating it, sharing it, distributing it, and then providing new kinds of application services based on all that information which is gathered either on an individual basis or in aggregate across large populations of sensors and devices.
Yeah.
And one of the things that's most interesting is the emergence of a whole new category of nodes, of the things of IoT, which are smart watches, smart thermostats, fitness bands, medical devices, countless ways in which data is being captured, analyzed, communicated up through the fog of access devices to the cloud of servers and infrastructure where all kinds of distributed applications can run. But when you look at those nodes, you find that there are some really important common characteristics. They almost always have to be low cost, low energy because they're often running on batteries.
Right.
They are commonly in unique form factors. They are supporting lots of new kinds of sensors, and they have this characteristic that I would call not just always on, but really always alert. They're always ready to be gathering information in response to what the user's doing.
Sure.
If we look a little more closely at the always alert node, we see that this is something which is sometimes an independent device. It may be an IC by itself that's in a fitness band, for example, or it could be a subsystem inside of a larger device. So it could easily be the always-on subsystem inside of, for example, a mobile applications processor.
Sure.
The issues are very much the same in terms of driving this always alert characteristic, driving this notion of very high energy efficiency, but it's also the case that these are often very computationally intensive problems because you have to do significant signal processing, significant communications processing in order to accomplish the goal.
Sure. So, Chris, I've done a lot of presentations before about the MEMS and sensor space, and it really seems like that has been a driver in all of this IoT stuff.
That's certainly right. What we find is that there are new kinds of sensors, and equally important, there's an explosion in the volume of sensors being used. So you find more sensors per device, more unit volume of sensors, and new kinds of sensors. In fact, you can see a range of different sensors from environmental sensors that may sample the environment maybe once a second, to motion sensors, the classic MEMS sensors of accelerometers and gyrometers and magnetometers. And then audio sensors, microphones, are very important because so much of how we gain intelligence from the world is in the audible domain.
Right.
Whether it's voice or environmental audio. And those are now up at the level of sensing tens of thousands or hundreds of thousands of samples per second. And ultimately, image sensors, really for vision.
Right.
And those have effective sample rates in the hundreds of millions of samples per second. So you have this huge dynamic range over maybe 9 orders of magnitude in terms of the sensing rate, how much data is coming into these nodes. And then on top of that, you have the question of how much computation is done for each sample.
Sure.
And that can range from tens, actually to thousands of operations per sample. So the total computational load, depending on the type of sensor and depending on the type of algorithm used to analyze that, can range up into trillions of operations per second. And
Wow.
it's that challenge of how do you keep very low energy while scaling to the appropriate level of performance that lies at the heart of innovation in these IoT devices.
So what does it mean for the device design itself? This has to bring up a lot of challenges for the design, whether it's in software or hardware.
That's right. In the IoT device, we see that there are very commonly 3 classes of functions you need to address. There's the question of sensing the data, of capturing it, of filtering it, of making it available for further computation. That's the second challenge, where you're doing significant amount of analysis, encryption, encoding. You're really analyzing the common impact from different kinds of sensors. So fusing that data into something meaningful in the context of the application of the device. And there's communication, often wireless communication, in order to move that data up into the cloud to communicate with other devices around it so that the data becomes useful. But when you look at all 3 of those things, sensing and computation and communication, there really is a significant workload that creates with some unique characteristics. Overall, they fall under the broad category of signal processing, and they fall in the category where energy efficiency is very important. But that then presents the challenge that existing solutions, existing microprocessor cores, are not typically highly efficient at all 3 of those things.
True, yeah.
And so depending on what mix of those 3 you need to support, you may find that you need to think in some new ways about the computational architecture to support all these kinds of things. And you also have to deal with the fact that different devices will have a different mix of those things. That some will do a lot more sensing and only a little bit of wireless communication. Some may be doing a lot of wireless and maybe doing relatively less in terms of the sensor fusion computation. And so you need to adapt if you're really going to get to the lowest cost, lowest energy solution.
Okay, so given those challenges, we have a Cadence logo at the bottom of these slides here. What's Cadence doing in this space?
Well, we're doing a number of things, but one of the fresh introductions that we're making is the new Tensilica Fusion DSP, which is our first processor core family focused very directly on the challenges of IoT devices, on the challenges of sensing, computation, and communication for this low-energy, low-cost domain.
Okay.
And we've done 3 things here with this product line. We're creating a leading low-power, high-performance DSP architecture, which has both the efficiency to address these always-on, always-alert nodes. It supplies a wide range of different computational models, including highly efficient floating point and very high throughput quad MAC, 4 MAC per cycle, integer DSP performance. The second thing we've done is created a new dimension of configurability and flexibility in configuring the core to have exactly the right set of features for the given application.
Okay.
And we've created a new set of configuration options so that you can have exactly the right core with no extra waste, no extra power, no extra silicon area. And we've created, thirdly, a comprehensive software environment around that core so that the design team in hardware and software can get to market quickly with highly efficient appropriate applications, libraries, and software development tools.
Okay, Chris, what's inside? What makes this tick?
Well, if we look inside, what we find is a novel, dual-issue, very long instruction word processor architecture. So it can issue almost any combination of two different operations in the same cycle, which gives us performance. It's based on our very popular Hi-Fi 3 architecture, but adds a number of new capabilities. This VLIW architecture is done in a special way that gives us very dense code. So we can issue multiple instructions, but those bundles of instruction fit within 16-bit, 24-bit, or 48 bits. So you don't have some of the code bloat that's traditionally associated with the phrase VLIW.
Yeah.
And at the same time, we provide in its rich instruction set this wide range of computational capabilities, characterized, for example, by the multiply accumulate, the max support, where in the baseline architecture, we have single 32 by 32 multiplies, dual 32 by 16-bit multiplies, dual 24 by 24-bit multiplies, and dual 16 by 16-bit multiplies. And that's just the baseline.
Okay.
Then we have a set of 5 different configuration options that allow that baseline architecture to be extended in the specific ways required by different combinations of features that you may want.
Okay.
We have a very efficient, high-performance, single precision, IEEE compatible floating point unit. And in fact, the floating point operations run in parallel with a 64-bit load store unit. So we have a huge amount of memory bandwidth in parallel with the floating point computation bandwidth. And that's one of the things that makes it much faster than the traditional microcontroller, even one that supports floating point, because of this parallelism and this bandwidth. The second package we call the audio, voice, and speech package. So this is a set of bit stream compression, decompression operations that allow us to be completely compatible with the Hi-Fi 3 audio DSP, and most importantly, give us immediate access to more than 140 Hi-Fi audio voice software packages from Cadence and from third parties. And so out of the box, the core with this configuration option then is a member of a world-class audio DSP family and has probably the richest audio ecosystem of any processor for the audio environment.
Nice.
The third thing we've done is offer the package of extended 16-bit multiply performance. So we bump it up from dual 16 by 16 to quad 16 by 16. And so for a very small increment in size and power, we get a large increment in performance. And this is particularly useful in things like communication standards, Bluetooth low energy, low-end Wi-Fi, as well as in voice algorithms, things like voice detection, voice recognition, voice processing. The fourth option package is the security package. This gives us a native instruction set level acceleration of the key 128-bit encryption functions that are commonly found to protect wireless communication and to keep communication secure and private. And it does it in a very low-cost way, but in a way that adds a lot to the throughput and to the energy efficiency. Moreover, it's more convenient for the design and smaller than bolting on an external encryption unit.
Okay.
And the fifth package is what we call the baseband bit operations. And this gives us bit manipulation for things like CRC generation, for bit scrambling and descrambling, for convolutional coding, a number of things that are commonly found in wireless baseband modem algorithms, and which allow the core, without external RTL blocks or other modem functions, to fully implement some of these key standards. So the combination of this very efficient and powerful base architecture and this choice to mix and match the different packages allows you to quickly configure something that has just the right amount of wireless communication support, just the right amount of security support, just the right amount of heavy-duty sensor fusion computation, perhaps in floating point, and the right sensing of signals, for example, voice signals or other signals coming from MEMS sensors, and to be able to reduce those signals and use those signals in a very efficient and programmer-friendly way.
Okay, so I think I understand the architecture and some of the advantages of all of this, but I actually want to use this in my system. So what does that look like?
That's a good question. And this is where we turn to saying a little bit about the Extensa Innovation Platform. The Extensa Innovation Platform is really this system of tools and methods that allow any chip architect or system architect or software architect to quickly configure and deploy the right configuration of a processor and its associated memories and interfaces and system peripherals, and to have both the hardware and the software immediately available that allows them to integrate it into their chip and develop and bring up their complete applications. So the idea here is that the system architect sitting at their laptop interface can quickly select and describe exactly what high-level features they want in their processor and make choices in seconds or minutes to iterate quickly and feed that set of choices into the Extensa processor generator, which almost instantly creates both the complete hardware design for that processor with its memories and interfaces and system peripherals, and the complete software development tools. For hardware, they get the pre-verified source RTL, they get the EDA scripts, they get the test suite and test benches so that they can fit it into their hardware flow.
Okay.
And on the software side, they have the C and C++ compilers, debuggers, simulators, RTOSes, libraries for all the popular functions so that they can immediately port, optimize, tune, and invent the novel algorithms that are going to run on their IoT device. And this method has been well worked by thousands of design teams in hundreds of companies. In fact, it's useful to look at just a tidbit of information on the kind of diversity of these DSP and other embedded processor cores that have come out of this flow over the last 15 years. We've delivered production versions of the Extensa processor family in 6,000 variants, of which 2,300 or more are DSP variants. There's more than 1,000 variants of this that are in production chips today, and those are shipping at a rate of more than 2 billion cores a year now.
Wow.
So it's really kind of an exploding segment of processing for embedded systems. I think because it really serves a unique need. It complements what is done in typical RISC CPUs, and it really can be used very often to offload and to take responsibility for the heavy lifting. The heavy lifting in DSP or encryption or bit processing or network processing or vision processing. And that ability to very efficiently do those tasks while working in a very standard software model is what's made it so popular.
Okay, Chris, I've got it on my chip, but what about the software side?
Yeah, software is critically important. I mean, software, after all, is the whole reason you put a processor into a chip in the first place.
Right.
And so having the right software for the range of tasks that you're trying to do is very important. And so what we've done is taken both this compatibility with the Hi-Fi family to bring all of that huge body of voice and audio software instantly available on the platform, but also developed ourselves and worked with third parties to create a large set of DSP math libraries, DSP audio framework, specific applications for voice trigger and face trigger, as well as a number of the key sensor processing software environments, all available onto the Tensilica Fusion DSP. So from day one, it has the richest set of software that we've ever had for a new family of processors and DSPs on the Tensilica platform.
Wow. All right, Chris, I know you can give me some examples. How are people actually using this kind of technology?
That's a great question. And happily, what we've seen is this rapid growth in the number of people using the Extensa innovation platform, using this kind of DSP technology to build high volume, high sophistication IoT devices. And so let me give you some examples here from a number of customers who've recently announced products that use Extensa DSPs like Fusion DSP.
Okay.
So for example, Megachips, a big fabless semiconductor company in Japan, is using our Extensa DSP to create their own proprietary variant of it that they call the Paraforce DSP, which they make the heart of a new family of IoT sensor fusion platforms they call the Frizz family.
Okay.
And they've been able to show very large gains in energy efficiency from using this configurability and extensibility of the architecture, more than 10x energy gains relative to the common choices.
Wow.
Or in another example, Seiko Epson is building a whole family of sports and fashion watches with built-in GPS.
Oh.
And by using Extensa DSPs for the GPS, they've been able to extend the battery life from approximately 12 hours active to about 30 hours active.
Wow.
So a big step up, not just in the theoretical energy efficiency, but
Right.
that's real usefulness.
Yeah, absolutely.
My day is longer than 12 hours.
Yeah,
so
mine is too.
some days it feels like it's longer than 30 hours. Or a third example is a case of really melding together wireless functionality, an 802 access capability, and sensor fusion capability. And Espressive, an up-and-coming Chinese fabless semiconductor company, has melded together a very complete sensor fusion interface with a fully integrated Wi-Fi radio and controller to build a very compelling Wi-Fi IoT device.
Oh, okay.
And so it has all of the interfaces, has all the radio components built in. And they don't sell the chip for $5. You can buy the system on Amazon for $5.
Wow.
That's a real milestone that you can get this kind of capability at the board level with software for $5.
Wow.
Volume 1.
Right.
That gives us an idea of where IoT is going. There's going to be all these new kinds of devices in new kinds of applications powered by this low cost, low energy, but so sophisticated software platforms. And that's why we're pretty excited about the space and why we think that the Tensilica Fusion DSP comes at a good time, building on the success we've had so far, but opening up this new dimension of configurability and efficiency for a new category of design.
So speaking of Tensilica, this Tensilica technology has been evolving for a long time, and you guys became part of Cadence 2 years ago. Give me an update.
Yeah, just about exactly 2 years. It's been a very smooth transition for us. I think that we haven't missed a beat in terms of the continued expansion of the footprint of the Tensilica technologies out in the marketplace, but now it's tightly integrated with all of the IP portfolio of Cadence. And Cadence has become now the number 4 IP provider by volume, by revenue, but we've maintained also a great deal of continuity. So it's really the same team working at the leading edge of processor architecture, DSP architecture, hardware implementation, compilers, libraries, audio applications, and some of these key enabling technologies to allow people to get to market. And the volume has been growing so satisfactorily. We have now this high run rate that really reflects the fact that these are becoming devices that everybody has, everybody uses. You probably have several Tensilica processors around you right now.
Undoubtedly.
And I think it really is reflecting the fact that Tensilica has become the number 1 DSP core architecture. It has become, after ARM, of course, almost certainly the number 2 processor architecture that you can license of any sort. And the number of licensees keeps growing. We're past 225 licensing companies. And in fact, the latest information is more than 1,200 different Tensilica cores from the Extensa family in silicon today.
Wow.
So we're pretty happy with the progress that we're making. And we think that this Fusion DSP is just one more step towards further proliferation and, more importantly, further innovation by this wide range of different kinds of chip and software and hardware developers around the world.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Chris. This was super cool.
Yeah, well, it's been great chatting with you. Thanks a lot.
Before we go, don't forget to click that link. There you can download a free white paper that further expands on this topic. For Chalk Talks, I'm Amelia Dalton. For more Chalk Talks, check out the EE Journal YouTube channel or the on-demand section of eejournal.com.